Let's get started. I guess this is a very exotic experience for all of us. But
if there's a lot of people,
yeah, let me announce a few rules. For the online teaching. During my session, I would like all of you to mute yourself so that we don't, crossfire. With a lot of background noises and everything. In case you have a question, you can use the raise your hand function, or you can use the chat function to put your question. I will try to respond, but in case we don't respond, we can again bring it to the office hour or after class for discussion. Today, I'm still teaching from a conference room at CMU, but if the campus end up closing, then I will be teaching from home, which will have less support from the crew, but hopefully we can still figure it out. Right? The lecture will be recorded. It will be posted right after. I will still making annotations on my iPad to make sure that the flow goes very naturally. And also, I will be trying to slow down the presentation, and so that we can make sure that the things are delivered clearly. Okay, we'll get started. Are you all ready? Just clap your hands or raise your hands. Cool. All right. I will be sitting instead of standing because, I may be pointing to the projector, but you'll also see me on the slides. So today we are going to enter a new topic, which is about structure learning and causal inferences, in graphical models and also in data modeling. So just to give you the bigger context, so far, except for the first few lectures, we usually assume that we have a good amount of knowledge of the domain, and then we use this knowledge to design, the model, right? And for example, you will see a mixture model, which we assume that we know there are multiple clusters in the data. And we could design a hidden Markov model where we assume that we know the dependencies between, the concepts. And also we could go even more fancy and come up with a deep neural network architecture and so forth. Another way people use domain knowledge is to design expert systems or knowledge graphs where concepts, entities are connected, in a graphical structure. But with all this, usually it's about knowledge first, and then knowledge drives the structure design. And that it's a very convenient way to encode common knowledges. But today, and I'm going to start coming from the other direction, this direction, in which we assume that we only have data, and we want to actually learn something from data, especially the dependencies or the correlations or the causal structures between entities, so that we can tell a story or we can use the knowledge to do something else, right? So this is about structure learning. And there has been a lot of study, in fact, for this topic as well, which is less mathematically elegant than what we've learned so far, where we come from a structure and also and then use that to learn a model for the data. But what I'm going to talk about are the subset of this topic where the mathematics are a little bit more clearer and more elegant. That involves learning structures with some limitation or constraints. For example, we can learn structures which is assumed to be a tree structure, and they actually provide a nice mathematical guarantee versus a non-tree. And then you can also learn, structures with directionality or without directionality, and we're going to talk about, approaches in this direction. Today, we're going to talk about the unstructured graph learning, which is in the form of a Markov network. And next week, we have 2 invited guest lectures talking about Bayesian network learning or directed graph learning, usually giving you a knowledge about the causal relevance between random variables. Okay. Oh, by the way, so I'm not going to talk about tree learning today. There has been some materials I provided earlier. I believe it's in lecture 3 or somewhere in the appendix. Basically, just to briefly give you a recap, when random variables, which I draw here, are connected, with a tree, for example, something like this. There is a way to learn such a tree if it is not given directly from data in a mathematically guaranteed way. The idea is to compute what is called the mutual information between every pair of random variables. And the mutual information is defined by, if you recall, what is that? It is the KL divergence between the joint distribution of xi and the xj versus the product of the marginal of the 2 nodes. Basically, this is to assume that these 2 random variables are fully dependent. This is to assume that the 2 variables are totally independent, and the distances measured by KL between them is the mutual information. And you can compute, pairwise mutual information for every pair of random variables, which is of complexity n squared. N is the number of nodes. And then after you have all this pairwise mutual information, you can run a maximum spanning tree algorithm to find the maximum spanning tree, okay, that connects all these nodes. And the resultant tree is actually, the most likely structure underlying the data. So this is called the Cholio algorithm. If you are interested, you can go to the appendix to look at the mathematics. Okay. Okay, so today we're going to talk about this topic, how to learn an undirected graphical model. And just to give you a context, this technique has been often applied in network research, where we want to really learn complex networks out of data. And here are some examples of typical networks. In social media, you want to learn networks among people, and here you can learn networks among websites or servers, IP addresses, and here there is a hidden network between maybe genes or proteins in a biological system. In some cases, the network is a real thing, but you don't know it and you want to recover it, such as the internet. It is a real network connecting IP addresses. In some cases, the network is an implicit one, such as social network, and where you want to really uncover it, from just activities of data. And in some cases, the biological one, well, we believe there is a real physical network, but no one has the ground truth to really know about it, and therefore you need to use the data resultant from the network, such as the gene regulation activities, that triggers the activation and suppression of a gene, and then reverse engineer network. Of course, there is a task, there's a challenge of how to validate them. I'm going to say a few words if we have time at the end of the class. Now, learning network, is a somewhat arbitrary practice in the good old days. It's a very, very kind of, how should I say, unstandardized heuristic. I think we saw this graph before, how to learn, for example, the social network of figures inside the Bible, right? We're talking about the co-occurrences of the names, in a page of the Bible, in a paragraph, or in a line or a sentence. All these can result in different networks. That basically suggests the need of a more principled approach. To make the problem more complicated, the network itself may not be a static entity. So in this case, we have, for example, data of voting records of a congressman, congresswoman, and inside, in the Congress, and their political or personal relationship may evolve over time. Therefore, you may be running into a network that is changing over time, and how to learn that is becoming even more interesting, but more challenging. And this is another example of a biological network where you can see the biological entity is evolving over time. And these are the two pictures of the expression of the same gene over the course of an embryo of the Drosophila evolution. And because the location of the gene is different at different time points, obviously their dependencies or their influences of other genes will be also changing over time, right? So how to learn a graph or a network, even an undirected one, from, say, nodal activities or time series data of nodal activities is the topic we're going to discover today. Right. So there are two approaches which are considered to be optimal, right? And one is based on maybe a heuristic, which allows you to search the structure space and optimize some kind of loss objective. It could be the log likelihood, but it could also be many other functions. This heuristic usually don't give you guarantee, but they give you very efficient algorithm, which you can quickly convert to a result. The other approach is a more principled one, with a more kind of explicit objective function and also algorithms, which are designed to optimize the loss function in a principled fashion, and very often with a convergence guarantee and a correctness guarantee. So today we're going to focus on the latter approach. So what is the key idea, between this, underlying this mathematically more principled approach of network inference? Well, one of the key idea is to really draw a equivalence between structure search, which is combinatorial, which is discrete, to a simpler search problem, which is to optimize the parameters, of some model in a continuous parameter space. Because there you can compute a gradient, you can calculate, the change of the loss function more conveniently, and also you can drive, iterative convergent algorithms more easily. So how to make this connection? Let's consider this social network. This is a little kind of a fragment of the social network. And on every node, you observe data such as voting yes and no in a binary form, or a real kind of vector, which gives you his behavioral activities or other things. It could be just fractional number of his interest on different options of activities and so forth. And remember, how do we model, a data set of either discrete or binary nodal value? One of the way to model that is to use a Markov random field, right? If you remember, the Markov random field defines potential functions, on clicks in the graph. And one of the representation is to define cliques only on singletons and on pairs of nodes which are connected, and then weight them with a potential weight. Now, if you look at this mathematical model, there is actually a implicit connection between the parameterization and the structure of the model, because each of the pairwise weight actually is attributed to a edge that connects the pair of random variables of interest. And if the value of that weight becomes 0, then you can just intuitively conclude that there is no edge between the set of random variables, the pair of random variables, right? So in a sense, if you can learn the value of the parameters, from data, and by looking at the magnitude of the value of every, pairwise potential weights, you actually could derive the structure of the graph. So that's basically where we draw the connection between structured learning and parameter learning. And again, just to recap, if you were able to learn, the parameters of the pairwise potential weights, then if you organize them in terms of a matrix, then there is a one-to-one correspondence of the zero and non-zeroness of this matrix against the structure of the graph. Okay, so that's the idea. Therefore, in this particular way of modeling the data, we are basically building a connection from structured learning to parameter learning. Okay, so now let's look at one of these Markov random field models. This is a model called multivariate Gaussian distribution. Okay, and it is not very obvious at the first sight that it is a Markov random field, because typically the way we write down a multivariate Gaussian distribution is to use this very standard form, where you have the mean vector and a covariance matrix to define the joint distribution. Now, without loss of generality, let's assume the mean to be 0. We can always shift the data to recenter it. And then let's introduce a new matrix, which is the inverse of the covariance matrix. And in that case, you can now rewrite the joint distribution of this multivariate Gaussian distribution in this form, which actually now exposes more explicitly the fact that it is a Markov random field. Basically, the numbers in the precision matrix Q, correspond to the weights of the singleton and the pairwise potentials in this continuous valued Markov random field. You can see that these QIIs correspond to the diagonal value of the precision matrix Q, and these pairwise potential weights Qij correspond to the off-diagonal numbers in the Q matrix in their corresponding positions indexed by I and j. I and j are the index of the random variables, right? And therefore, Gaussian graphic model is a pairwise Markov random field, and the covariance matrix carries structural informations, of the graph, in an indirect way, because only when you are able to invert it to turn it into precision, then you can read off the structure of the graph connecting all the axes, from Q. Okay, that's basically written here. Now, if it sounds like the problem is solved already, if you want to learn the graph, you can just compute the covariance matrix. This theta equals to what? Equals to xi and xj, and we'll just sum over them, and you get the precision covariance matrix, right? So, and then we invert it, and we get a Q already, right? So sounds like the problem is solved. In fact, if you look at both the theta, sigma, and the q, you actually could have two graphs. Originally, people didn't even bother to learn about the q. They just basically directly expect the precision, the covariance matrix sigma, and when there is a zero entry, in sigma ij, then obviously it suggests that x and the xi and xj are marginally independent of each other. Therefore, you could directly draw a graph which is known as the correlation network. Okay, but the correlation network isn't the Markov random field structure that I just talked about in the Gaussian graphic model a few slides ago, because in there, it is the configuration of the Q matrix that defines, the graph structure. And the key differences here is that a zero in the Q matrix corresponds to not the marginal dependencies, specified by the sigma, but a conditional independencies between x and the xi and xj given the rest of the nodes in the graph. And this difference is important because if you remember, when we define the topology of the graphical model in our first two lectures, we actually already specified explicitly that absence of edge inside a graphic model correspond to conditional independencies, not marginal dependencies, because they will lead to a lot of downstream nice effect, such as factorizability in the graphical model and causality if they're directed and so forth, right? So it is the, conditional independencies inside, the graph that is more interesting, which correspond to the Markov network definition. When we say, okay, we like a Q over sigma, but it doesn't make the problem harder because Q simply equals to sigma inverse. We can just first compute the sigma from data and invert it. We get a Q, we still get a structure, right? So that seems to be an algorithm already. So now, does it really work? Okay, in the class I ask, but because we are having some challenge now in real-time interaction, let me answer that for you. Inverting this sigma is not so difficult, conceptually, but computationally it can be very difficult. First of all, if you have, remember, this algorithm inversion is of complexity n cube, not n cubic. Okay, not quadratic. Therefore, if you have a larger network, say a few thousand words, then inverting that that covariance matrix can be very, very expensive. Right? And secondly, in larger graph, if you don't have enough sample, then your sigma matrix may be degenerate. Therefore, you may not be able to invert it, right? So there are a number of difficulties. Therefore, there is a need to bypass this inversion step and say, can we directly learn the Q? Okay, because in fact, inside Q, if it is a really meaningful structure, you see actually a lot of zeros. Therefore, you don't actually expect them to be a full matrix, and therefore it is not likely to be resultant from inversion of another full matrix. Right? There should be a direct mechanism to learn the Q with such a a structure sparsity encoded already. That basically becomes a very, very interesting challenge, but also an opportunity. So we see the need for sparsity, right? It makes empirical sense because natural networks for genes and for people should be sparse. Otherwise, it's not even meaningful if you say everything is connected to everything else. And also, it makes statistical sense because that makes it possible to learn, from high dimensional data with not enough data points, if you assume it is sparse. Okay, so let me first introduce a heuristic algorithm, and to make this work, at least learn the structure directly possible, and then let's talk about the statistical underpinning behind it. So there is an algorithm. Okay, so I said that there is a simple heuristic built on the LASSO algorithm, and this is the mathematical formula of the LASSO, where we basically are solving this linear regression with an assumption that the beta is actually constrained, okay, with a certain constant, right? Or maybe actually there are different ways of constraining it. This is just one way to constrain, but there are other ways. For example, you can do a L2 norm and so forth. Right? Anyway, so the idea of LASSO is that you are going to now solve, imagine if we project this idea into a graph node and the kind of setting, you can assume that I have one node of interest, and all the other nodes, okay, which we call them collectively x minus I, to be the input, into this target node, xi equals to beta x minus I, okay, plus a noise. Then if you are able to estimate the beta, then they will give you basically the weights of all these other nodes to this target node, okay? And the LASSO idea is that we're going to do a sparse regression of all the other nodes, into this target node, the blue one from the green ones. And once that is estimated, we're going to get a structure like this. Okay, this is just a very simple sparse regression. Okay. And in the literature of regression, there has been a fair amount of a theory for this particular estimator. And one of the explanation of what's happening is that you can write down this regularized regression in the form of a constraint optimization problem. These two are equivalent to each other, where you basically assume a standard regression subject to that the coefficients are constrained, in a box. Okay, this is known as the box constraint, or the L1 constraint, which looks like this. So in this graph on the lower left corner, you see this ellipsoidal kind of a loss function shape, which actually defines the loss function from here. Your goal is to minimize, remember this space is the space of beta. Suppose we have just two-dimensional beta, right? And by changing the value of the beta, you're going to minimize, for example, the loss function from somewhere into here. But then here, the diamond box is corresponding to the constraint, meaning that whatever beta you solve, it has to be staying in this diamond. Then the joint solution of a optimization and also the constraint has to be the intersection of these two little figures. Therefore, they intersect in here, right? And this graph also explains why the solution will be intuitively sparse, because if you look at the shape of this constraint, which is a diamond, it is the extreme point, the corners in here, which is more likely to be touching the loss function of the other part of the optimization. And therefore, when we're touching here, then by definition, the beta 2 is already equal to 0. The beta 1 will be in here. Right? So that's the idea. If you imagine a higher dimensional space, this high dimensional ellipsoid will be touching the high dimensional diamond in some corner space which correspond to many beta values to be 0. Right? So that leads to basically something like this. You are going to end up with a regression where only a few of the beta will be non-zero, and that leads to a, so to speak, a very sparse neighborhood of the y in the collection of the x. And there are some guarantee, some theoretical proof to guarantee that if the true kind of a regression, setup, was known, then you have a high probability of recovering the truth if some conditions are met. So we're going to, skip the discussion of the conditions. Okay. So now if you do, the regression once, you get something like this. You can do it again for another node, and then you get another set of neighborhood of the second node, and you do on, and in the end, you magically end up with a graph which allows all the nodes to be connected in a sparse way. There is one caveat which needs some special attention. For example, when you do regression over this node, and you will be having its neighbor like this. And then when you do regression of that node next, then you will be redo basically, this particular edge and may have a different beta value. And which one is true? If one is 0, the other is not 0, then which one do you choose? Well, you use some kind of formula, to either threshold it or to select one of it. Okay. So this is an algorithm known as the graphical lasso. Basically, you are going to do the lasso regression for every node with respect to all the other nodes in the whole collection, and you end up with a graph. And Meinhausen had a very, very famous and widely referred paper proving that this procedure will have a high probability of recovering the true, beta value or the true structure of the graph. Okay. So you may wonder, this looks like a very weird algorithm. Instead of estimating the Q, I'm now estimating the neighbor of every random variable using a linear regression. Why this is working? Okay. Well, you can look at the paper in here, and which give you a very, very kind of in-depth theoretical discussion. But here I want to give you a more high-level understanding of what is happening. Okay. Why, for example, a Gaussian graphical model, leads to can be equivalent, to a sequence of linear regressions, in terms of recovering the structure in the graphical model. Why it is happening? So to understand that, you want to look more deep into, the algebra of a Gaussian graphical model. So here I rewrite the expression of a multivariate Gaussian distribution and also the underlying Gaussian graphical model. Let's look at the behavior of all their parameters. Okay. So if you notice, the two key parameters are the mu and the sigma. Okay, and remember, mu is a vector, and the sigma is a matrix. Okay, they basically have all the secrets of what we call a structure of the corresponding Gaussian graphical model. Now let's look at a division of these parameters. Say we are interested in dividing the entire set of random variables into two subsets. Let's say this is x1, this is x2. By the way, here x1, x2 correspond to two subvectors, not necessarily just a single random variable. The whole thing is a whole vector of many random variables. Okay, then you can correspondingly divide the matrix also into this structure, right? And let's give a name for that. And with these two subsets of the whole set, you can now ask questions like, what is the marginal distribution of the second subset? what is the conditional distribution of the first subset of random variables given the second subset, and the reverse, and so forth, right? So this is standard manipulations of a multivariate Gaussian distribution. It turns out that after working out the algebra, you can easily get the following thing. The marginal distribution of a subset is expressed in this form, which can be easily read off from the given parameter of the whole distribution. Basically, it is just a subvector and a submatrix of the original mean vector and the original covariance matrix. And the conditional distribution of a subset of random variable given the others correspond to another Gaussian distribution whose mean, conditional mean, and the conditional covariance can be derived from the original mean vector and the covariance matrix using the following formula. You can see that they correspond to some reassemblage of the original corresponding building blocks in the mean vector and in the covariance matrix. So these are formulas that is nice to remember. Okay, how do you basically directly write a conditional mean and a conditional covariance given the original full joint mean and joint covariance? Okay, and there is another technique people often use, which is about how to invert a matrix. Here, I'm not going to say too much. It's very algebraic. Basically, if you have a matrix of the following structure, you can apply inversion kind of a matrix, inversion diagonal matrix on the left and on the right to invert this one into to turn this one into a diagonal, and then diagonal matrix can be inverted very easily, right? And then you can basically get the following kind of expression that the diagonal matrix, the way to invert basically the original matrix is to first diagonalize it using this, and then invert the diagonal matrix, and then you basically get a analytic expression of the inversion of any arbitrary given matrix. And there are also different ways of diagonalizing it. Therefore, you can have this two equivalent expression of the inversion of the original matrix. Okay. And that actually leads to what is known as the matrix inversion lemma. That establishes the relationship of the inversion of a submatrix versus elements in the original full matrix to be inverted. Okay, we're going to use it for some applications later on. This is known as the matrix inversion lemma. Remember, in here, why it is already potentially useful. If you look at my earlier equation in here, to write down the conditional mean and the conditional covariance, you need to manipulate submatrices in the original full matrix of covariance. And then here, you already need to apply operations like inversions to the submatrices. And that's where this kind of technique will be used to make the computation very explicit. Okay, so now let's look at our, go back again to look at our Gaussian, multivariate Gaussian distribution. Here is the covariance matrix of the Gaussian, and they correspond to this kind of a general expression, of the component matrices. And if we divide our random variable in such a way that we only worry about one of the variable I and also all the rest of the random variable x minus I, then we want to define, the partition of the original covariance matrix in this way. The first element is just a single scalar, and then here you have a n-1 dimensional submatrix. n minus 1 dimensional vector and n minus 1 dimensional vector, right? And then using the matrix inversion lemma, remember Q equals to inversion of the covariance matrix, you actually can get the following expression, okay? Where, you can actually see, where the Q and the Q minus 1, correspond to, in this original expression, okay? So in here, you can see that each of the, components in the precision matrix can be expressed as some operation over the submatrices in the original covariance matrix, okay? Okay, so now with this, we can write down the conditional distribution of a particular random variable in this multivariate Gaussian, given the rest of the random variables. And here are just the expression of the conditional mean and the conditional covariance. It's kind of scary to look at the equations, but you can go back to the standard formula I gave in the previous slides to reconstruct all these equations. By assuming, in fact, I already copied these things in here. They actually are used to derive this equation. By assuming the mu to be 0, you can actually come down to a very, very simpler form, which looks like this. Okay. So remember, the conditional distribution of P of x given x minus I is a one-dimensional Gaussian distribution, which can be parameterized by a mean, which is expressed in here, and a covariance. And it is a one-dimensional Gaussian, therefore mean and the covariance are both, a scalar. Okay. All right. So now let's see, how does this look like? So just look at the connection of this conditional distribution versus what we expect from a typical standard regression, right? So in here, basically, we're saying that x comes from a Gaussian distribution, and the mean of the Gaussian is defined by this matrix. Therefore, x basically can be expressed as Q right. So that's basically expression, and this sigma basically comes from a normal distribution with a 0 mean, and this one being a noise. Right. So this expression, which is directly coming from the conditional distribution of a single random variable in the multivariate Gaussian, given the rest, is no different from what people expect from a linear regression. Okay. Therefore, in a linear regression, what we do is to learn say xi given equals to beta xi minus I plus lambda, and then beta subject to some constraint, and we learn basically the beta to be a vector of 0 and non-zero components. They translate to basically something about the Q matrix, because if we look at this Q vector, for every node xi, this Q vector is what? It's basically corresponding to the original Q matrix, which, remember, encodes the Markov network of the Gaussian graphical model. This Q vector, which is the regressional coefficients of a particular random variable Qi is actually a particular column or row in the Q matrix. Of course, they are rescaled by a diagonal number, a Qii. But if you look at, ignore the value of the Q, but only the zero and non-zeroness of the Q. What if I have a particular, say this is a Q vector, or maybe this is the, let's call this a beta vector. First, imagine this regression. If in the beta vector, I have one of the component to be 0, okay, meaning that this one has a particular number 0, then that also corresponds to, in the Q vector, this particular number to be 0, right? In terms of zeroness and non-zeroness, not just the value of that. I hope you can see this connection. And then once we learn that a particular component in the Q vector is 0, then we can also safely draw the conclusion that a particular number in this bigger Q matrix to be also 0, right? Therefore, each time you learn a Qi, okay, which corresponds to the ith column in the Q matrix, you actually correctly learn a column worth of numbers in the precision matrix. And if I run Q from 1 to n, then you can gradually learn all the columns in the Q. Okay. And the Q, by the way, is a symmetric matrix. Therefore, all the rows of the Q are the, can be equally, filled in. Therefore, you can basically learn a matrix of the Q in this way. Right. So what I meant to say is that this zero and non-zeroness, resulting from a LASSO regression, for the auto-regression functioning here, allows you to, iteratively and sequentially learn the precision matrix Q in terms of their non-zero entries, being entries being 0 or non-zero. Okay. Okay. So that's basically, the intuition behind the algorithm. Just to recap, originally, we say that, the conditional independent structure, of a Gaussian graphical model is in Q, not in sigma, but Q could be correlated, related to the sigma by a inversion. And then we conclude that this path doesn't go through because you have all this mathematical issue. We want to learn the Q directly. And then we say that, there is a way to establish every column inside the Q. Okay, to correspond to a regressional coefficients of the auto-regression problem Qi versus xi versus x minus I, in this simple regression form. And therefore, by learning the beta, you learn the Qi vector, and then you learn the Q matrix. Okay, so this is a rather indirect way of learning the Q. And here, to learn beta, you need to put a sparsity constraint so that you can consistently recover the 0 and non-zero value elements of the Q, and you don't actually, draw consistency on the magnitude of the Q numbers. And that's why we call this algorithm structure learning. We are only caring about the 0 and non-zeroness of elements inside the Q, not the magnitude of that. Okay, and there is a guarantee that that 0 and non-zeroness can be correctly recovered using this algorithm. The value is a different situation. We can discuss later if we're interested in that. Okay, so that's basically the whole story of this so-called graphical lasso regression algorithm. And there has been a number of alternative formulations solving the same problem, which I will quickly run through, but I'm going to skip the math due to the time limit. The algorithm we just heard about is known as the Myhausen and the Billman algorithm, which is to do a cyclic lasso. And once you do n of them using the neighborhood selection, you are going to recover the whole Q matrix. Right. There is another slightly more sophisticated algorithm which directly solves the Q, okay, by computing first the covariance, sample covariance matrix directly from data, and then use it to define the following optimization problem, which is actually a maximum likelihood estimation in the original Gaussian graphical setting. Okay, but this Q matrix gets regularized in a L1 way so that they become sparse. And then there's an algorithm which is very similar to the graphical regression, which again goes down to learning the Q from every column. But in here, there is a single loss function defined over all the columns, rather than for every lasso, you solve them separately. Therefore, this algorithm is iterative, and you're going to resolve basically the regression when you have some other kind of parts of the Q matrix estimated. Therefore, there are some dependencies between different lasso problems, which gets you to a more stable solution. But again, due to time limit, I'm not going to discuss the technicalities in here. Okay, so what we've discussed so far is to solve a model known as the continuous multivariate Gaussian distribution, which is also known as the Gaussian graphical models, where the random variables are continuous. What if the nodal value, every node or every random variables are discrete, such as in the social network, we model people how they vote, right? So it's a binary value. Well, similarly, at least from a symbolic perspective, writing down a Markov random field for discrete nodes is no different from a continuous node. You still have a pairwise Markov random field, and you can still write down a joint distribution using singleton and pairwise potentials weighted by the parameters, right? And also the weights can reveal the structure of the graph depending on whether they are 0 or not 0. And intuitively, you can guess that the value of the theta can actually also be recovered by a auto-regression type of mechanism, where you pick every time one of the x and then do a regression function over the other x, okay? But in this case, x are discrete, not continuous. Therefore, you cannot use a simple linear regression to make the connection. What is needed is something called a logistic regression, where you model the conditional likelihood of discrete random variables rather than the continuous random variables. Therefore, the conditional of one random variable given other random variable is no longer a Gaussian distribution, it is a logistic distribution, a regression function. Okay. So, and we know how to solve logistic regression, therefore the algorithm still goes through, and people can also prove that it gives you consistent estimation of the structures. So that's a discrete graph. There are even more interesting scenarios of maybe vector valued nodes. For example, if I have a graph where every xi is not a one-dimensional continuous number or a binary discrete number, but is itself a vector, okay? And maybe this guy is also a vector. and how to draw a connection between whether there is a node or not. And in fact, these two vectors may be of different dimensions, just like you are having interest in 5 activities, and another guy have interest in 10 activities. How can I draw a connection between you two, right? So these are, again, making the estimation of the graphical models more kind of complicated. And I'm not going to discuss the mechanism here, but there are kind of papers discussing how to estimate a graph of this kind using partial correlation computations and other techniques. Okay. So this is a whole domain of area for graph estimation using either partial correlation computing or regressional type technique to estimate, the neighborhood of every node. And typically, this forms a family of structured learning algorithms which enjoy some nice statistical guarantees. So with that, I'm going to move into applications of our basic technique to some more interesting setting so that you can estimate graph structures in more challenging scenarios. This is just a very quick review of some of the early work done in my group and also in the community. For example, I mentioned about the need for estimating, evolving social graphs, right? And why evolving social graphs is, interesting and also harder to estimate. Well, it's interesting because the graph, in real world is evolving. Therefore, your data coming from a time series of, nodal activities are not necessarily ID samples that you can just collapse and then run a maximum likelihood estimator of a single structure for all the data, right? And then how can we actually do estimation in this scenario? It's actually becoming quite challenging because if you look at a particular time point, say T star, and you look at how many samples are available for this particular graph, in the extreme case, you have only maybe just 1 examples, right? And in fact, each particular graph may have just 1 examples. Therefore, estimating, a model out of 1 data point is never a good idea, in statistical estimation, right? So, but that doesn't mean you cannot do anything with that, because one key kind of insight, for this type of structural estimation problem is that these different graphs over time are not totally independent of each other. Okay, in fact, they are highly dependent because they evolve over time just by modifying a small subset of nodes and edges. So if that's the case, can you actually come up with an algorithm which can estimate in time-specific graph using the entire set of data examples? So here, I want to introduce a few algorithms. Okay. One algorithm is known as the kernel-related L1 regularized regression. Okay. Again, it is a neighborhood selection algorithm on every node against others and runs cyclically. And therefore, the loss function look very much the same of what we learned so far on IID examples for a single graph. But the breakdown of this loss function is a little bit more interesting than a IID estimator. Here, when summing over a time series of node examples or vertex examples, we're going to now introduce a weight function. The weight function is defined over 2 time points. Okay, one is the time point t of your estimation. You want to estimate a network at time t. The other is the time t prime, where the example is coming from. And the weight function is kind of measuring and considering the distances between these 2 time points. Okay, and then you do a weighted sum of the conditional likelihood of a node of interest I given the rest of the node. Okay, and the weighted sum is weighted over time points. That's summed over time points. And the intuition is like this. Suppose that I'm interested in this graph at time t, and I have one example. But I also acknowledge that all the other examples which are not from this time point t may be relevant to the graph at time t after all, because it is coming from a graph that is not too much different from time t. Okay, the closer the time is to the t of interest, maybe the example is telling more about the graph of time t. Right? Therefore, what you can do is to do this kind of reweighting, okay, of the examples, so that if you focus on a particular time point in here, you can kind of treat all the time points examples, but downweighting the examples that come from a time different from the time of estimation. Okay, so this is kind of an intuitive kind of estimator or a strategy that you would want to use to blow up the number of examples from 1 to all the examples you have in hand, just by introducing this weight function. Okay, so this is a typical non-parametric technique. When we do kernel density estimation, this is again a very, very common technique to build a density estimator by weighting samples either close or far away from the center of the gravity. Right? And again, the loss function can be a logistic loss or can be a conditional Gaussian loss, depending on you modeling conditional continuous random variables or discrete random variables. And then you again do the kind of neighborhood selection for every nodes. And the algorithm basically look the same as if you do the standard graphical lasso. The only exception is that your samples are getting reweighted. So this is a very, very seamless algorithm that is reusing most of the existing technique. And there is a nice set of theoretical guarantee that tells you that if your samples are evolving according to a certain rate of change, and also the dependencies between random variables are nice behaving, which are described in these conditions, you actually could get the similar guarantee as if you are treating IID data from this whole data set. Okay, so this is the guarantee where tells you how you can recover the structure of even the evolving graph for every single time point with a high confidence. There is another algorithm which is similar in spirit, but use a different technique to capture this in continuity. So it was published in this paper. It's called temporally smoothed L1 regression. And you can see the loss function is a bit different from the previous one. The previous one are using a loss function which are reweighting the examples in here and sum over time. Okay, it is really for just one graph at time point t and sum over all the examples. In here, the strategy is to estimate all the graphs together, okay, from time t to time 1, okay? And therefore, the samples, that defines the conditional likelihood from x1 given xi given x minus I is not going to be reweighted. They literally will be, just the sum of their conditional likelihood without reweighting. But because now you are estimating all the networks together in a single optimization function, you are allowed to directly measure the differences between the neighboring graph. So here we introduce a two sparsity. One is that every graph needs to be sparse. And then here we enforce that the differences between the adjacent pair of graphs in time to be also sparse. So what's the intuition? Well, this is to assume that the evolution of the graph structure is smooth or gentle over time. Therefore, between two graphs that are just next to each other in time sequence, they should be minimally different from each other. Therefore, there is this sparsity preferences. Right? So graphically, you can see we do graph lasso, like all these graphical lasso in a single equation. But then because for a particular edge, like this one, we introduce the time differences to be small, so that they tend to be, if an edge present in a graph before, then it is more likely to be also present in the graph next. Right? And using convex duality, you can rewrite this regularized, slightly more complicated regularized regression formalism using a constraint, box constraint, optimization, where here are the two constraint sets. One is the same constraint we see before, on every single edge, okay, to be basically, constrained inside a diamond space. And the other is known as the total variation differences, where the differences of the two edges or two weights gets also constrained down to a small number, okay? And you can run, a number of different algorithms, projection gradient and other things to achieve the solution. It's a little bit less efficient than the graphical lasso for every single graph separately, but still it is solvable to the order of a few thousand nodes. And again, there is a way to establish a consistency guarantee that the estimated results are recovering the true graphs if certain conditions are met. Okay, so if you are interested in looking at the theoretical analysis of these two algorithms, I encourage you to go read this paper in Annals of Applied Statistics, where some of the proofs are provided. Now let's take a quick look of what you get out of this slightly more elaborate algorithm, which can be quite fun, in fact. Because in the past, there isn't really a very, very convenient and mathematically safe way to estimate evolving graphs. With those algorithms, now you can, and let's see what the result look like. So we apply this algorithm to a set of social network time series data. The first one is the Congress voting record, and in a particular time period. In fact, in the period of 12 months, and it's about the voting record of the 100 senators. Okay, and here is the outcome of the evolving graph. It's kind of interesting to read these graphs. If you're interested, you can see the paper. They display something that people kind of expected, and some are more interesting. So for example, the graph itself, for all the three kind of time points that I would choose to show a very explicit partisan structure, right? You have the Democrats, the Republicans, highly networked within among them, right? But what's more interesting is that there are some nodes which are in the middle, meaning that their voting behavior are in the kind of the middle between the Republicans and the Democrats. Again, these are a data set about 10 years ago. You may not know all the senators already. I actually don't remember who they are, but there are some names which is worth looking. For example, who is in the middle and who is so forth. Now, there is a guy, for example, this Senator Shafe. And if you look at his own neighborhood, at a particular time point when he was just entered the Congress, he was actually highly associated with the rest of the Republicans, right? Then, after a few months, his voting records start to show connections to the other side of the aisle. And in fact, after a few months, he is becoming more associated with the Democrats. and less associated with his Republican colleagues. I believe this guy was either lost his re-election or changed party affiliation to the other side, after his first term. But this graph actually shows a very interesting estimation, that is kind of predictive of his political movement, during this particular time period. We have another candidate, Senator Ben Nelson, who demonstrated the opposite behavior, coming out of the Democratic Party to the Republicans, after a certain period of time. Right. Another application is in biology. Again, biological networks are also evolving over time or over different biological contexts. Here, we have a set of biological examples coming from a collection of cancer, the breast cancer collection. Okay, the breast cancer cell lines that we study demonstrated a few different disease stages. They come from normal stage, malignant stage, and in fact, my colleague has been working on using some medicines to revert the oncogenic cells to its normal form. And here, basically, she shared with us the reverted cell lines from the malignancy. But this reversion was only from a pure morphological kind of observation. You put the cell under microscope, they look normal. Are they really molecularly normal? Is not known, okay? So she basically gave us a problem. Can we use a network inference to determine whether those cells in here, which are morphologically normal after drug treatment, really normal in terms of their gene expression networks, okay? But again, the problem becomes very difficult because we don't have enough samples to estimate the network at every time point or every evolution point. And therefore, we want to establish a procedure which can still use all the examples, but hopefully estimate all the networks in a dependent fashion. Right? So for example, here I have 5 networks, and I'm going to introduce a formula which penalizes the total variations of networks that is adjacent in their time points. By the way, this total variation regularization is particularly useful when you actually know the dependency structure between the networks, not the dependency structure between the genes, but the whole network. They evolve over time. If you know how they evolve in terms of the time sequence, you can directly introduce this loss function according to the edge. Right? The original non-parametric technique, which use weighted sum of all samples, cannot make use of such a dependency structure. So with that, we actually come up with an estimator, which are like this. Here we have all the networks, and here we have the sparsity constraint, and also the total variation constraint for the differences between networks. And this part is the regressional kind of loss, of graph reconstruction. And at the end, we actually were able to estimate these 5 networks. I'm about to finish. Please keep unmute, and I will wrap up in 3 minutes. So these are the estimated networks, from 5 different cancer stages. And we actually present this back to the collaborators. And she actually was able to find that some of the, for example, this network in T4, which is known to be the cancerous stage, is indeed quite abnormal because there are elevated network activities in this tumor-related cell functions. But when she looked at all these reverted cells, there are 3 different types of reverted cells. She was able to actually find out which particular network activities are suppressed and which are not to be suppressed, and therefore determine whether the cell is at the molecular level truly becoming more normal or actually not normal at all, even though they are morphologically, in terms of shape, look like normal. So this is kind of a application which has been published and adopted in different studies to leverage graphic models' ability to estimate time-evolving network structures to determine cellular functions. And we also have follow-up work to estimate more fancier networks and more complex scenarios, such as directed graph over time evolution networks. Or if you have missing data, how do you estimate network structure? And I mentioned earlier, if you have multi-attribute data, let's say every node is a picture, for example, how do you estimate their network? There are various different algorithms coming into that. So to conclude, today, we learned a set of algorithms which allows you to estimate the connectivity or the topology of a Markov random field graphical models. They usually take advantage of the neighborhood selection algorithm, which allow you to turn the combinatorial structure search or the matrix inversion estimation problem into a sequential linear regression style problem to give a more efficient but also consistent solutions. And then the technique can be further extended into complex scenarios such as time series, time varying network scenarios to allow multiple graphs to be estimated based on very small sample sets. So with that, I'm going to wrap up today. Let me see on Zoom, do we have other people? Good. Well, unfortunately, I haven't figured out how to make this lecture more engaging by taking questions and having answers. But let's try to get used to this. Hopefully, in the next few lectures, we can make better use of Zoom to allow questions and allow more live discussions online. Okay. Please write your response and feedbacks in Piazza or directly write to me in email. And also make sure that if you already received the class survey, you want to really finish it and send back to the TA so that we can also make adjustments and improvements accordingly. Okay, thank you very much.